Hello and welcome to the reading of Rocks, Fossils, and Time. Earth is constantly changing. Nothing on its surface is truly permanent. Rocks that are now on top of a mountain may once have been at the bottom of the sea. To really understand the planet we live on, we must include the dimension of time. We keep track of time with an invention most of us take for granted, the calendar. The calendar is based on the movements of Earth in space. One spin of Earth on its axis is a day. One trip around the sun is a year. The modern calendar is a great achievement, refined over thousands of years. People who study Earth's history also use a type of calendar called the geologic time scale. It looks more like a book than a wall calendar. Rocks are the pages of this book. Some of the pages are torn or missing, and the pages are not numbered. Even so, geology gives us tools to help us read this book. Rocks and layers. We look into Earth's history by studying the record of events preserved in the rocks. Most rocks on Earth's surface are sedimentary. They formed from sediments, bits of older rock that were broken apart by water or wind. Some of these rocks contain fossils. Sedimentary rocks form particle by particle and layer by layer. Gravel, sand, and mud settle on the bottoms of rivers, lakes, and the ocean. The layers pile up, one on top of the other. You saw this in the sedimentary basin you created in class. Superposition provides an important clue to the relative ages of rock layers and the fossils in them. A layer must be older than any layer on top of it. Horizontal layers form when sediments settle from water or air, the principle of original horizontality. But many layered rocks are no longer horizontal. Why is that? The rocks moved from their original horizontal position. Events such as a mountain formation and earthquakes can fold, bend, and tilt sedimentary rock layers. Rock layers are also called strata. Stratigraphy is the science of layered rocks, which includes how layers relate in time. Figuring out the order in which a group of rocks formed, with the oldest on the bottom, creates a relative time scale. Geologists can infer the order in which these rock layers formed. The oldest rock layers are generally underneath younger layers. Putting events in order. Think about these 5 historical events. TV becoming common in homes, World War I, World War II, the Wright brothers' first airplane flight, and astronauts landing on the moon. Let's try to put these events in order using logic, common sense, and a little knowledge. We can infer that World War I occurred before World War II. We know, or we're told, that millions of people watched Neil Armstrong on TV when he walked on the moon. TV had not been invented when the Wright brothers flew their airplane. So we can order these 3 events: the Wright brothers' flight, then TV becoming common, and then the landing on the moon. Looks something like this. By gathering information and making comparisons, we can put all 5 events in order. Because we have written records of when each event happened, we can also put them in order by using numbers. The Wright brothers' flight occurred in 1903. World War I lasted from 1914 to 1918. And World War II lasted from 1939 to 1945. Television came into our homes in the 1950s. And Neil Armstrong walked on the moon in 1969. Written records exist for only a tiny fraction of Earth's history. Understanding the rest of the history requires gathering data, comparing information, and making reasonable inferences. You may not know the date of the Wright brothers' flight at Kitty Hawk Beach, but you can use clues to figure out whether it happened before or after the first moonwalk. The geologic timescale. Scientists do not measure Earth's history in familiar units like days, months, and years. When we talk about Earth's history, time is measured in millions and billions of years. The geologic timescale divides geologic time into manageable chunks. To develop a geologic timescale, geologists in the 19th century started by looking at fossils in different rock formations. Certain kinds of fossil shells were always found in layers older, aka lower, than layers with plants. Dinosaur fossils show up only in layers above layers with plant fossils. The geologists could use fossils to develop a relative timescale for the history of Earth. They inferred that species with shells had been living on Earth long before plants appeared, and dinosaurs appeared only after plants. Study the modern timescale presented here. Eon is the largest division of geologic time. Eons are divided into smaller categories. Eras are broad spans based on the types of animals on Earth at that time. Paleozoic means ancient animal life. Life in the Paleozoic era included trilobites, corals, brachiopods, early fish, and early amphibians. Mesozoic means middle animal life. It is known mainly as the age of dinosaurs. Cenozoic means recent animal life. Mammals dominate the Cenozoic era. Periods subdivide eras. Periods are based on significant rock formations. For example, the Cretaceous period, right here, is named for English chalk beds of this age. In Latin, creta means chalk. Epochs are subdivisions of periods. The Tertiary and Quaternary periods are divided into epochs. English geologist Sir Charles Lyell lived from 1797 to 1875, came up with these subdivisions after he studied marine sedimentary rocks in France and Italy. Index fossils. William Smith, lived from 1769 to 1839, was an English surveyor and engineer. As a crew dug a new canal, he studied rocks in the canal's path. The exposed rocks puzzled him. Several exposures of limestone did not appear to be the same. Also, some layers were not horizontal, but were tilted and bent. Smith tried to figure out a way to make a correlation between rock layers at different sites. Smith collected fossils from the limestone layers. He noticed that each different limestone layer had its own particular kinds of fossils. He could determine whether two samples of limestone were from the same layer by studying the fossils he found in each. Some fossils showed up in several layers, but Smith found certain fossils present in only one layer. These unique index fossils could be used to identify a layer. Furthermore, he inferred that all layers containing a particular index fossil must have formed at the same time. Take note. Both the Paleozoic era and the Mesozoic era ended in great extinctions of many species of organisms. What could that mean for the end of the Cenozoic era? Correlating rock outcrops. Scientists compare index fossils to figure out which rock layers formed at the same time. Smith now had a way to determine the relative ages of the rock layers. He could also predict the order of rock layers below the surface. Smith drew a column of all of the rocks below the ground in an area. His drawing was accurate, even though there was no one site where all the rocks were exposed. These predictions were a great help in planning digging projects. Smith's work established the disciplines of stratigraphy and the study of Earth's history. Geologists now use index fossils to relate rocks across great distances, even between continents. Inferring rocks underground. By studying rock layers that were exposed at the surface, Smith successfully predicted the order of rock layers underground. Fossil succession. If we begin at the present and look back into older and older rock layers, we soon reach a level with no human fossils. If we continue back through time, we reach levels with no fossils of flowering plants. Going even further back in time, we find rocks with no bird, no mammal, no reptile, no four-footed vertebrate, no insect, no land plant, no fish, and no shell fossils. We eventually get down to rock with no animal fossils at all, only bacteria. Finally, we reach a time when Earth rocks have no fossil evidence of life at all. 3 concepts are important in the study and use of fossils. Number 1, fossils represent the remains of once living organisms. 2, most fossils are the remains of extinct organisms. They come from species that are no longer living on Earth. And number 3, the kinds of fossils found in rocks of different ages are different because life on Earth has changed through time. Stratigraphy is the study of rock layers. Stratigraphy exposes the Earth history of a place going back many hundreds of millions of years. These three concepts are summarized in the law of fossil succession. The kinds of animals and plants found as fossils change through time. And when we find the same kinds of fossils and rocks at different locations, we know that the rocks are the same age. This law is important to geologists who need to know the ages of the rocks they are studying. It is basically a timeline of fossils. New forms of life. How do scientists explain the changes in life forms observed in the fossil record? Early explanations suggested natural disasters that destroyed life every so often. After each catastrophe, life began again. In the mid-19th century, both Charles Darwin, 1809 to 1882, and Alfred Russel Wallace, 1823 to 1913, came up with another idea. They proposed that older forms of life produced new forms of life. Darwin's basic idea was that species evolve, or change over time, or they die out. Darwin's theory accounted for all the diversity of life, both living and fossil. This theory of evolution has been refined and modified as new information has been added. The new information supports Darwin's basic idea. Living things have changed through time, and older species are ancestors of newer ones. Fossils of a known age. Detailed study of many rocks from many places has produced a collection of index fossils. Index fossils allow geologists to pinpoint the age of a rock layer within a few million years. An index fossil must meet certain criteria. The organism must have had a wide geographic range, have existed during a brief, well-known period of time, have been abundant, and be easy to identify. One example of an index fossil is Tetragrammatus. It was a small animal that floated in the early Ordovician Sea that covered the Colorado Plateau. Because it floated, it had a wide distribution. It only lived during the Ordovician period. It is an important index fossil for Ordovician rocks. If someone handed you an unknown rock sample that contained the fossil Tetragrammatus, you would know that the rock formed in the Ordovician period. Most fossils are found in sedimentary rock, often formed on sea floors. These ammonites were marine predators that became extinct along with the dinosaurs. So these are what ammonites look like, the background here. Fossil records. So this is just a depiction of all of the different time periods where we can find these different organisms. We've got animals and we've got plants. And then this is a drawing of a Tetragrammatus, and it would be roughly 1 centimeter big or across. So it's a pretty small organism. The absolute time scale. How did geologists get from a relative time scale to an absolute time scale? How did they determine these dates? Well, Earth is about 4.6 billion years old. The oldest fossils are from rocks that are around 3.7 billion years old. The first abundant fossils with shells occur in rocks that are about 570 million years old. The last ice age ended 10,000 years ago. Geologists and paleontologists in the 19th century had only crude ways of estimating how old Earth is. In 1896, they got a new tool for measuring Earth's age. Antoine Henri Becquerel, from 1852 to 1908, a French physicist, found that the element uranium changed into lead through a process called natural radioactive decay. His discovery was the first step in finding a numeric age for rocks. Not all elements undergo radioactive decay. Only the ones that contain radioactive isotopes, such as uranium. Some isotopes decay rapidly, like in seconds or days. Some can take millions of years. Only isotopes that take a long time to decay are useful to date rocks. It takes 700 million years for half a uranium sample to turn into lead. This number is the isotope's half-life. By measuring the ratio of uranium to lead in a rock sample, geologists can calculate when the rock formed. At last, rocks could be dated absolutely. Absolute dating. Dating rocks is complicated and requires a well-equipped laboratory. Two commonly used methods are potassium-argon dating and carbon-14 dating. Potassium is an element in many rock-forming minerals. Some of it decays into argon. Potassium-argon dating can be used on young rocks, a few thousand years old, and on rocks that are more than 2 billion years old. At Dinosaur National Monument in Utah, a sloping rock formation contains fossils of hundreds of different organisms. Scientists can determine the age of sedimentary rocks by studying the fossils found in them. Carbon-14 is better for dating a different group of objects. Carbon-14 constantly forms in Earth's upper atmosphere. It finds its way into all living things. After an organism dies, the carbon-14 in its tissues begins to decay. Carbon-14 is useful in dating only materials that were alive during the past 50,000 years. Only igneous rocks can be dated absolutely. Geologists measure the potassium and argon in a rock's minerals and calculate when the rock became solid. Dating sedimentary rocks. It is sometimes possible to accurately date rocks that are not igneous. The age of igneous rock that is next to sedimentary layers can be determined absolutely. This information can be combined with relative age information to come up with an age for the sedimentary rocks. Examine the diagram below. Which rocks formed first? What about last? Geologists use potassium-argon dating on the basalt dike in the diagram, which is right here. It is 23 million years old. This tells us that the sedimentary rocks, which had to be in place for the dike to form, are older than 23 million years. By combining absolute age information with relative ages, geologists can figure out the dates of each new area of study on Earth. This reading was adapted from Fossils, Rocks, and Time, U.S. Department of the Interior / U.S. Geological Survey, USGPO publication, 1996-421-4280. Dating rock layers. A dike of melted rock, or magma, pushed up through the sedimentary layers and spilled out at Earth's surface. By dating this igneous rock, F, scientists can determine the ages of layers A through E. The red hot rock is a lava flow that originated deep underground and has reached Earth's surface. As it cools, it will harden to form brand new basalt rock. Think questions. Number 1. Explain several ways that fossils provide important data to geologists and stratigraphers. Number 2. Look at the chart on page 58 showing when organisms appeared on Earth. What changes do you notice in the animals as you look from the most ancient times to the present? Number 3, using the same chart on page 58-59, what changes do you notice in plants over time? Number 4, give an explanation for the changes seen in organisms over time.